Okay, it will be 200 by 3K. Now you can remove this portion. This portion is not valid now. This portion 15 is connected to the emitter now. Let me draw it again. So this is emitter part. Here it's a 15 volt. Now you need to calculate IC. Why IC? Because you have to replace this by the equivalent circuit. In that I need IC DC. Because I need to calculate beta RE there. Why we are doing this DC analysis? By doing this DC analysis, we can convert the equivalent circuit of transistor or BJT, right? We have seen just now that in the equivalent circuit of the BJT, we need beta RE, that is R pi. Beta is available with us. RE we calculated VT by ICDC. I need ICDC, means the IC collector current in DC operation, right? It is fine. Now, where is the VBE? B to E. Here is the VBE. This is the VBE given over here. You need to calculate this IC. So, I'll apply the input current analysis. So, it will be 15 plus 0.7, 15 plus 0.7 and divide by wait a minute. Let me clear some part and make some space, then I'll show you. Wait. So let's do it like the current IE is coming to like this. So 15 plus minus 470 of IE. Perfectly fine. I'm coming to this. I'm getting plus 0.7 volt. And here the current IB is coming like this. Is it okay? So I'm getting positive 200 by 3K into IB. IB is perfectly fine. And at the end I'm getting minus 5 equal to 0. Now I need to calculate IE or ICDC because IE and ICDC both are equal. And definitely in this case they will be equal because beta is very large, that is 800. So what is the relation between beta and IC? IC equal to beta IB. Is it okay? So I beta is IC by beta. IC by beta. I can replace this IB by IC by beta and beta is 800. I can replace this IE by IC also because I need to calculate only IC over here. Let me make some space. Are you getting? So come now. So this 800 and this will go 4 times. So ultimately you are having 15 minus 5 10 minus 470 IC plus 0.7 plus this is 0.7, okay, plus this is 4 and 12 IC by 12. Am I correct? And this is in K actually. Is it okay? Equal to 0. So this is 10.7 470 IC minus IC into 1000 by 12. This is like this. So when you calculate IC, you will get 10.7 divide by 470 minus 1000 by 12. So this will be nearly 83.33. So you will get IC. So it will be nearly IC equal to 26.64 milli. IC is, you have calculated IC. Is it okay? Now let me erase some part. You calculated IC. Remember 26 milliampere. Okay. Now I can remove this circuit. I have to show you now. We will calculate beta RE because the DC analysis is over. Now we'll switch to the AC analysis. Okay. In the AC analysis, we turn off all DC sources, right? And we will solve the circuit. Let me show you the AC analysis now. But before do AC analysis, you need to calculate RE, transistor RE. Is it okay? So RE is, what was the formula? VT divided by IC DC. So RE is VT by IC DC. We know VT is 25 or 26 milli, just near to 26 milli. And IC DC you have calculated 26 milli. So it's 1. The value of this is 1 ohm. Now you need to calculate beta RE. So beta RE is nothing but 800 into 1. So 800 ohm. Now you can replace this by equivalent resistive network. Now I'll do the AC analysis for this. Okay. So to start with the AC analysis, why I'm going to do the AC analysis? Because I have to calculate V0 by Vi. And this V0 is the AC. This Vin is also AC. That's why, right? So the equivalent circuit of this is, now I'm drawing the equivalent circuit for this first. The equivalent circuit of this is beta RE, that is 800 ohm, perfectly fine. The current IB is coming like this. Okay. This is the emitter, and the emitter is looking like 470. This is the 470, and this directly grounded. Here at 470 I am taking V0. This is the collector portion, directly grounded, but the current is incoming from the emitter. Current is incoming. See, this IB will be outgoing. And what about IC? This will also beta IB times will go outside from the circuit. This is the circuit you have. This is the equivalent circuit of the transistor, but you have to do this circuit parameters also. This will be 200k in parallel with 100k like this. Okay, and they are grounded because the DC portion is grounded. So this 200 in between this point and ground. So 200 in between this point and ground. 100k between this point and ground, this point and ground. And over here you have V in. This is your equivalent circuit. Now we are taking output over here also. Okay. So you have to calculate V0. Let's change the direction because I need to calculate, or I need to show IB plus IC is IE only. So this is like this. This plus this will be IE. When current will be over here, I'll take it V output. Okay. So how to proceed now? We don't know IB. We know the beta. It will be 800 of IB. Is it okay? Again, we can resolve this if we want. 100k and 200k, they are in series. So, they are in parallel. 200k divide by 300k, k got cancel, 0. This is 200 by 3k. So the equivalent of this you can replace now by only one. Let me do it clearly. This is 200 by 3k. Okay. 200 by 3k. Let me do it. Wait. Here the current is IB. And here the current is 800 IB. Is it okay? Now this IB is current coming to IC. Here 800 IB current is coming to over here. So here the total current coming is 801 of IB. Is it okay? So if you calculate V0, wait. So for this circuit, V0 will be, tell me, V0 will be 470 multiply with 801 of IB, 801 of IB. Is it okay or not? Is it correct? Now you have to divide it by IB only. So but you are calculating for what? You are looking for voltage gain, that is AV. AV is V0 by V in. Is it okay? So V0 portion is over. Let me write over here. V0 is 470 801 of IB. Now I need to calculate V in. How to calculate V in now? Tell me. To calculate V in, you will apply the KVL in the input side of loop or mesh, whatever. Means you will start from V in, you will go to the ground. Always start from the V in and go to the ground if you want your current or your voltage drop or whatever it is. So let me show it over here. So V in, I'm starting with V in. Perfectly fine. You are going into this, you are having drop 800 IB. You are going into this, here you are getting minus 470 and your current is 801 IB. This is your current equal to 0. Starting from V in and going to the ground, you are encountered with this two terms. So finally your V in will be, if you will calculate V in, it will be 800 plus 470 into 801 of IB. Like this. Is it okay? Now, with respect to this 800 is very less. 800 470 times, and this is only one time. This is very less amount. So your V in is nearly 470 into 801 of IB. Means your gain is, this is your V0, 470 into 801 of IB. And this is your V in, 470 into 801 of IB. So they will cancel out. AV is equal to 1. But this is not exact equal to 1. This is nearly equal to 1. Okay. So this is the question based on the common collector. Earlier we identify what is the answer. That is 1, because this is the voltage buffer. Okay. Now this is the procedure to solve small signal analysis. First the DC part and then AC part. We'll take some more problems. So let's take another problem, and this is the GATE problem, 2008 problem, right? GATE 2008. And this is 2 marks problem. Actually this is the statement linked question. So total marks are 4. Means 2 marks, 2 marks, 2 questions. And the circuit is given over here is, let me draw the circuit within 30 seconds. I'll try to draw it. 20K, 10K. This is 10K, 20K, 3K, ammeter. Ammeter is connected with 2.3K in parallel with capacitor. So obviously this will be common ammeter, right? Here it's connected with C2 coupling capacitor, and here connected with 3K like this, taking output 3K, 20K applied with 9 volt VCC. This is the input. Input capacitor, and here applied with, I'm sorry for this, V in. Okay, this is the circuit. This is the entire circuit given over here. This is the small in which we have to do the small signal analysis, because DC and AC part both are given over here. And the question, 2 questions, but before that some conditions are given. The following transistor circuit VB equal to 0.7. The voltage drop is given over here between base and ammeter. 0.7 given over here. RE is given 25 milli volt divided by IE. They have given RE in this format. And beta and all the capacitors are very large. Beta is very large. These things are given in the question. Now, the first part of the question is the value of DC current. The value of DC current gain. DC current gain. They're asking the value of DC current IE is, sorry. They're asking the value of DC current I. DC current IE, the first question is. And you have 4 options for this. 1 milliampere, 2 milliampere, 5 or 10. So first I'll solve this part. This is the DC current. Means definitely this type of question we have to start with the DC analysis only. Is it okay? So let me start with the DC analysis. When you will do DC analysis, all AC part of the circuit will be turned off. All capacitor of the circuit will be open. Okay. So let me do the DC analysis for this. DC analysis. This is 20K, 3K connected with 9 volt. The circuit is like 2.3K. Over here, the capacitor is gone from the circuit. This is the circuit. This is 10K. Is it okay? And this over here, you have V0. And apart from this is gone. So the 3K is useless. Right. Now here is the IE. This is IE is nothing but IE DC, whatever they are asking. So again, this is the potential divider. Again, you can find the potential over here. So this will be 3 volt. This will be 3 volt over here, and the equivalent of these two will be 20 into 10 divided by 30. 20 into 10 divided by 30. It will be 20 by 3K. So this will be 20 by 3K. Now you can remove this part. This is the input equivalent, right? Perfectly fine. Now 9 volts will be connected already with this. Here it is 3K. This is your circuit. Let me make it clear. This portion. So this portion is like this. 20 by 3K. Whatever this combination is there, now I took the equivalent of this. 3 volt, the voltage across 10 volt, 10K. 9 into 10K divided by 30K, it will be 3 volt. This is your circuit. Now the question is, we have to calculate IB and we have to consider this portion 0.7 they have given in the question. So proceed. So, okay, let me erase some part. It's unnecessarily problem. Wait a minute. So 3 volt minus 20 by 3K of IB. This is IB minus 0.7. Minus 0.7. And here you are getting 2.3K of IE equal to 0. Equal to 0. Is it clear to you? Now remember, in the question they have given IB is very large. So, sorry, beta is very large. When beta is very large, IB is nearly equal to 0. So I can remove this IB from the circuit. So you will be remained with, this is the 0. 3 minus 0.7, it will be 2.3. And it will be 2.3K of IE. So IE is nothing but 1 milliampere. So first portion answer is 1 milliampere. This is very easy 2 marks question. Now in the second one, they're asking, let me erase it first. This is the first portion. They're asking for the DC current IE. We calculated IE. And one more thing, please remember always, when beta is very large, the current, base current will be 0 in the circuit. When base current is 0 in the circuit, IE will be equal to IC in the transistor, right? So first portion is over and we got 1 milliampere IE, and that is DC. Correct? Now it's time to do the AC analysis for this circuit. Let me make it clear. I will do the AC analysis. The DC is over. And the second question is actually, let me write the question first, then we will do the AC analysis. For that question, we need an AC analysis. The mid-band voltage gain of the amplifier is approximately, they're asking voltage gain. They are asking voltage gain, and voltage gain is nothing but V0 by VI. So V0 is AC, VI is AC, so we need AC analysis of this. So to switch into the AC analysis, you should be knowing, or you should have knowledge, equivalent circuit of transistor. The transistor equivalent circuit will be beta RE, and here you will take like this, and so you need RE. RE is given over here 25 milli divided by IE. IE is 1 milli, so this is 25. This is 25. Now you don't have beta in your hand, so what you will do? So we'll keep beta as it is. Okay. Now let me draw the AC equivalent circuit. The AC equivalent circuit. RE is 25 ohm we have calculated. Now let me draw the entire AC circuit. So now V in will come into the picture. This DC source will be grounded. The capacitor will be short. The capacitor will be short. So this is grounded. So in between this point, if this is base point over here, so between this base point B and ground, you are having 20K as well as 10K. So I'm drawing the equivalent. 20 by 3K. 20 by 3K is over. Across B point, V in is applied. V in is applied. Perfectly fine. Here, this is the transistor territory. In the transistor territory, you are getting beta RE, where RE is 25 calculated. Over here, this is the emitter, and that emitter is grounded. See, this is grounded, right? Because you shorted the capacitor. So emitter is grounded. Now come to the collector one, and in the collector one, this is beta IB. The collector itself having two resistances. One is from point C to ground 3K, one is point C to ground 3K. So you can resolve them and it will be 1.5K. And here your V0, you have to calculate your V0 over here. Okay, now this is your IB, friends. This is your IB, friends. You need to calculate AV. AV is nothing but V0 by V in. So first calculate what is V0. The V0 is C. This is the closed circuit. This is the closed circuit. This current will not come to this portion. It will go into this. So this IB current is coming from downwards and dropping itself into 1.5K. So V0, the polarity of V0 we are calculating it this way. So V0 will be definitely negative, and it will be beta IB into 1.5K. Perfectly fine. This equation is okay. Now we'll divide by VI. What is VI? Again, we'll start with VI. We'll go to the ground. Okay. So VI over here, VI minus IB into this, IB into beta into 25, and this is ground. Everything is over. So this is equivalent to this. So you are getting this beta IB into 25. So beta IB and this is IB will cancel out. So it will remain with minus 1.5K divided by 25. Okay. So when you will divide it, you are getting minus 60. So your voltage gain is minus 60. Is it okay or not? So this is the common emitter. In the common emitter, the gain is 180 degree phase shifted. So it's true. By the way, the 4 option we are getting, and in all 4 option, I'm getting minus, 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 and minus. So option D is correct for this. Is it okay? So let's take another problem. It's also very interesting problem, and this is GATE 2012. 2012 problem. Okay, and 1 marks problem. This is 1 mark problem, and the problem is the equivalent circuit is drawn of transistor. This is R pi, we have seen, right? This is collector, this is collector, this is base, and into the collector R0 is also connected with this current source, like this, and it's like this. Okay, R pi 3 C B, and here the current is IB. Here the current is IB, and the question is, the current IB through the base of a silicon NPN transistor, the IB is given 1 plus 0.1 cos 10 to the power 4 pi t milliampere at 300 K. 300, this is the room temperature. The R pi in the small signal model of the transistor is, then R pi is, and your options are 250 ohm, option B is 27.5, option C is 25 itself, and option D is 22.5 ohm. The R pi. Is it okay? So R pi is what? So R pi, we have seen, this is nothing but beta Re. You need to calculate Re, and Re is Vt divided by IC DC. Is it okay? So what is Vt, friend? At room temperature 300 K is given. The Vt is 25 milli. What is IC/DC? Can I write this IC/DC is beta IB DC? Can I write it? Yes, I can write it. What is the IB DC? What is the DC? Remove the AC part. The DC is only 1. So this is 1 only, given in milli. So this is 25 milli. Milli will cancel out, divide by beta. Re is 25 by beta. Just place the value over here. Beta into 25 by R. 25 by beta. Beta will cancel out. You are having 25. Option C is correct. You are getting 1 marks. Okay. So let's come to the next problem, and this is GATE 2014. GATE 2014 and 2 marks. Okay, and the problem given is, I'll take 45 seconds. 12 volt, 33K, 11K, grounded, 5K, 10 ohm only. This is RS given. This is RE given. 1K. And RE in parallel with capacitor. This is grounded. Okay. And over here I have 1 microfarad. And this is V in. I'm applying over here. And over here I'm taking output. This is 1 microfarad given. This is your question. 33, 5K, 10. This is ohm. Okay, here the student make mistakes over here only. They'll write it 10K and everything will be spoiled. Okay. Here the value is 1 millifarad. Now the question is, I'll read the question. For the amplifier shown in the figure, the BJT parameters are VB 0.7 always, 0.7, beta is 200, thermal voltage VT is 25 milli. The voltage gain V0 by Vi of the amplifier is the voltage gain V0 by Vi of the amplifier is, it's this fill up type. In the volt they are asking. Right? Now, definitely we have to do the AC and DC analysis. This is a small signal analysis type of circuit. So first I'll do the DC analysis for this circuit. Okay, let me change pen. Is it like this? DC analysis. I'm going to do the DC analysis, DC part of this. So the DC part is 12 volt as it is, 30K, 5K, 11K, like this, and this is here 10 ohm, and this portion remaining RE will be grounded because we are making it okay. It will be also reflect over here because you are making capacitor of open circuit. RE will be there in the circuit. It is 1K. Everything is fine. The capacitor is removed. Everything is removed. This is the circuit. Okay. Now to this circuit we can resolve this portion again. Here the voltage will be this will be 3 volt, I think, right? 3 and 4. So this will be 3 volt. And the equivalent of this two 11 and 30K is 11 33 divided by 44. 11 4 33 by 4K. 33 by 4K. Now I can remove the remaining part because I made it equivalent. I can remove this 11K. This is my input circuit now. My input circuit is 3V. This is 33 divided by 4K, and this is 12 volt over here now. This is grounded. Okay. I need to calculate IE or IC. Here beta is also given. I'll apply the input in input mesh, the KVL. So 3 minus 33 by 4K of IB minus 0.7, and here I'm having 10 and this 1K. So this 10 of IE, 10 of IE is equal to 0. Is it correct? So this IE I can write IC, no problem at all. This IB I can write IC divided by beta. So IC divided by beta is 200. So IC is unknown in the circuit now. So this is 2.3 equal to 33K by 4 plus 1010 IC. 1010 IC. And this is divided by 200 also. And this is 2.3. So overall 33 into 5 divided by 4 plus 1010 of IC, and this is 2.3. Correct. Let me erase some part, then I'll solve it. So this is 2.3 into 4 divided by 33 into 5 plus this is 4040. This will be your IC. When you will solve this, you will get, so you will get IC equal to 2.2 milliampere. 2.2 milliampere. So IC part is over. So now RE. RE is VT divided by this. VT is 25 milli divided by 2.2 milli. So it will be milli will cancel out. It will be nearly 10 point and something. Is it okay? Actually it will be 11.23 ohm. So this is your RE. If this is Re, what is beta Re? You will multiply this quantity with 200. Okay. Wait a minute. 11.23. Multiply with 200. So it will be 5.4K. I'm sorry, it will be 2.2K. Is it okay? So this portion is over. You calculated beta Re. Now we'll put the values into the AC signal, AC analysis. Okay. Let me erase it. Now the DC part or DC analysis over. Now we have to calculate voltage gain. That is the AC voltage gain. That's why we have to do the AC analysis for this circuit. I hope the concepts are pretty clear to you now, right? So let me do it. Now the AC analysis for this. The AC analysis need beta Re. We calculated it 2.2K. The AC analysis will make it short. So this part will be over. Here it will be 10 ohm only. This will be connected with beta IB. This is beta IB, the collector, and the collector is connected with 5K up to ground. So this is 5K. Here I'm taking V0. This is the input part. The input is 33K and 11K. They are also connected up to the ground, and equivalent is this is 33 by 4K, and here we are applying V in. Is it okay to you? In this circuit the current is IB. Now you need to calculate V0 by VI. This is your voltage gain. What is V0? Calculate it. This is grounded. So your V0 is this current into 5K. So beta IB into 5K, but sign is negative because the polarity of V0 is like this, but actual voltage of polarity is opposite to original one. Is it okay? So this is V0. Come to the V in. For V in, simply procedure, have to start from this point and you have to go to ground. So V in is nothing but 2.2K of IB plus this 10 into this beta, and this is 200 IB. This is like this. So it is kind of 2.2K plus this is 2K IB. So it is 4.2K IB. This is V in. This is V in. Now the voltage gain is minus beta IB into 5K minus beta IB into 5K divided by 4.2K of IB. IB will get cancelled, KK will get cancelled. So finally its AV is minus beta 5 divided by 4.2. Put the value of beta. Finally you are getting minus 238. This is the voltage gain for this circuit. So I hope the concepts are pretty clear to you. In the next module we'll see some more problems based on this AC and DC analysis. Okay. So again I'm telling you how to proceed it. First you need to analyze the DC part of the question. In the DC part, what will become at output? You will get Re from the circuit because you need beta Re to replace this BJT as the equivalent resistive circuit. This Re will come because of DC analysis only, because Re is nothing but Vt divided by IC DC. So to calculate Re, you need the value of IC DC. So for the IC DC, you will do the DC analysis of the circuit. After doing this, you will be available with Re. Now you will replace this entire BJT circuit with the equivalent model. And equivalent model we have seen it. This portion will be beta Re. If this is emitter, this is base. In the base the current is IB. In the collector the current is beta times of IB. And this is your emitter. Is it okay? So this is the equivalent part of the BJT only. Now we are having the circuit elements also. In the AC analysis, the DC part will be 0, means grounded. So if you will ground this part, so base to ground, you will have 33K, you will have 11K, 11K. They are in parallel. So I resolved it and took over here 33 by 4K. At this portion, the capacitor will be short and the voltage is Vin. At the output stage, from collector to ground, you have 5K. This is collector to ground, you have 5K. And collector is directly connected to V0. So this is V0. Is it okay? So this is the procedure. So I hope it's clear to you. So we'll meet in the next. Till then, take care and bye.
In the previous session of the control systems engineering, we have studied the transient response analysis in detail along with the problems and concepts. In this particular session, we are going to study Rao's criteria and root locus. We have already seen the theory and some problems related to Rao's criteria and root locus. In this session, we'll be revisiting those concepts and revising the concepts with the problems that are asked in GATE examinations and different high-level examinations. So, let us go forward and let me tell you what are we going to focus on. So, Rao's criteria. First, we will go to Rao's criteria's problems and concepts. Rao's criteria is the algebraic method to understand the stability of the system. So, basically, in Rao's criteria, you get the idea about the stability, but which is very discrete. Like if for Rao's criteria analysis, you have stability or instability. So basically, when you are given a system, you either can say the system is stable or unstable or maybe critically stable. So this is what the idea you get from Rao's criteria, which is not the case with root locus. So basically this is the algebraic method. Okay, and this is geometric method to find the stability, which I had already mentioned. Now, geometric method allows you to see into the system and actually allows you to understand how much is the stable system is given. I mean, whatever system is given, you cannot just say that system is stable, but you can also say that system is more stable or less stable. You can relatively compare two systems according to stability or instability. So this is the main difference between root locus method and Rao's criteria method. So in Rao's criteria, we make up Rao's array and decide whether system is stable or not. And in root locus method, there are certain rules to draw a root locus, which is nothing but the locus of all the roots or all the possible roots of that particular characteristic equation in the S-plane. And according to that locus of roots, you can decide whether system is stable or not. As you change one of the parameters in the root locus diagram or root locus method, the diagram of root locus changes, and according to which you can decide changing the parameter makes system stable or not. The root locus method is more insightful and visually it is possible to see if system is stable or not. So this is a qualitative method, and this is a very discrete method which can just tell you if system is stable, unstable, or critically stable. With this introduction, we will go forward to the problems of Rao's criteria. Let us see a very first problem. So problem number 1 is the open loop transfer function of unity feedback control system is as given. So this is open loop transfer function. Okay. Now you need to find out the condition on this gate for system to be stable. Okay, that system should be stable, and you need to find out the range of values of k. Now you can find this out by simple Rao's array method. Okay, as this is open loop transfer function, we need to convert this into closed loop transfer function and see the characteristic equation. As this is g of s and assuming h of s to be unity, okay, because it is given unity feedback, so h of s will be 1. Okay, so basically this is my G of S, and this is the unity feedback. Okay, there is no feedback. I'm given this transfer function value as this is negative feedback, and this is my reference value, and this is my C. So basically I need to find out the closed loop transfer function, which will be G of S divided by 1 plus G of S. As H of S is 1, it will be 1. So if you find this out, you get K divided by S cube plus A plus B S square plus AB S plus K. So this is the characteristic equation of the closed loop transfer function that you have got. Now, once you have found out the characteristic equation, let us build a Routh array to check if the range of K is one of these options. Okay, let me erase everything on the slide and let me write. So our characteristic equation that we found from closed loop transfer function was S cube plus A plus B S square plus ABS plus K. Now simply Routh array is built like you first write the highest degree S. So we have written S cube, and just below it write the 1 degree lesser power of S. Now to build the Routh array, you write the alternate coefficient from S cube. So you write 1 on the first place, then you write the alternate coefficient, that is AB, which is the coefficient of S, and then the next alternate, which is nothing. So you won't write anything here. Then you start from the coefficient of S square, which is A plus B, and go to the next alternate coefficient, which is K. As there are no further coefficients, you won't write anything ahead. Now you need to find out the coefficients related to these particular spaces. Now this value here can be found out by multiplying this value multiplied by this value minus this value and this value's product. So if you do this, A plus B into AB minus K divided by A plus B. So this is how you can find out this term. Let me write A plus B into AB minus K divided by A plus B. So this is how you can find out this value. So the next value here, now the values here are nothing. So these are actually 0. So if you try to find a value here, it is A plus B into 0 minus 0 into 1 divided by A plus B, which is nothing but a 0. Okay. Now you need to find out this value here, which is this value multiplied by K minus 0 into A plus B divided by this value again, which gives you this into K minus 0 divided by this value, which is ultimately K. Hope you are following. So basically, whenever you need to find out any Routh array coefficient just below, let this be S raised to M and this is S raised to M minus 1. This is P, Q, A, B, and if you need to find out X, so X is equal to A into Q minus P into B divided by A. Okay, so this is how you calculate this value. This is then C and D. You need to find Y. Y would be A into C minus P into D divided by A again. So this is how you find these values. So we have found out these values. Now let us go back to problem. For system to be stable, we know that the signs of all the values in the first column of root array should be same. Now for this system to be stable, here the signs should be positive, because the sign of 1 is positive. That means all the signs here should be positive. Okay. Now let us find out the condition on k. Let me just write down that a plus b should be greater than 0. Also, this value here should be greater than 0. Let me write here in only. So if you solve this, you get, if you multiply on both sides by a plus b, which is actually positive, you will get a plus b ab minus k greater than 0. So that means a plus b ab is greater than k, and also k is greater than 0. Let me erase everything. So we have got a plus b greater than 0, then a plus b into ab greater than k, and k greater than 0. So if you find out the condition on k, which comes out as 0 is less than k and k is less than a plus b into ab. Okay. So this is the condition on k for this system to be stable. So simply in the step 1 we found out the closed loop transfer function from the given open loop transfer function. Then we saw the characteristic equation, and according to the characteristic equation we built the Routh array, and after the Routh array we needed all the first column signs to be same, which was positive in this case, and then we found out the condition on k. So the correct option here is option C. Let us go to the problem number 2. This is again a very good problem, a little lengthy problem. I want all your attention on this problem now. This is a little critical problem. Let me just tell you a trick to solve this problem. Not the trick, the concept. So basically when you have a Routh array, say here we have s raised to 5 and s raised to 4. So the coefficients, if you put on all the coefficients, you will get 1, 2 and you will get 3 here. 1, 2 and 3, and the next alternates 1, 2 and 50. Okay. So now if you try to solve this value, you get 1 into 2 minus 1 into 2, 0 divided by 1. So you get 0 here, and you get minus 12 here, because 1 into 3 minus 15 into 1 divided by 1. So you get minus 12. Now you needed to solve this value, but this value is 0, and ultimately if you try to solve, you get 0 into 2 minus, so you get 12 divided by 0. So in the denominator you are getting a value 0 which is not defined, and that's why you cannot actually keep this 0 here. Now you need to put epsilon in place of 0, and epsilon is just greater than 0. Okay, a very small value which is greater than 0, and then you can solve this value using this epsilon, and this value will be function of epsilon. Then you keep on solving all the first coefficients, and then you put limit on epsilon to go to 0 and find out the sign of all these values, and then you find the stability. So in this question we need to find out, for this characteristic equation given, the roots that lie on the right hand side of the S-planar. Now you know whatever sign changes, if you get two sign changes in this particular column, then you say there are two positive roots. Or if you get one sign change only, you say there is one positive root. So you need to check the signs of all these numbers in the first column, and then you need to check how many sign changes are there, and according to it you are going to get the positive number of roots. So let us build the rows array. Let us build it again. So we have, I'll need more space here. So s raised to 5 and s raised to 4. Then let me draw a long line. Then you have 1, then you have 2, and then you have 3. Next you have 1, then you have 2 and 15. Now let us build the next value, which was 0. So we are going to put epsilon in that place, where epsilon is just greater than 0. We are going to put this value, which is nothing but minus 12. And now we will build this value. So this value is nothing but 2 into epsilon plus 12 divided by epsilon, which is nothing but 2 epsilon plus 12 divided by epsilon. And if you find out this value, you get 50. Okay? In the next step, you need to find out S1's coefficient here. So this is this value into minus 12 minus 15 epsilon divided by this value. So you ultimately get, so let me solve it here. So you get minus 24 epsilon minus 144 minus 15 epsilon divided by this value. 2 epsilon plus 12, and numerator will be multiplied by epsilon. Now, if you write this value here, you get epsilon, and you can add these values, minus 24 and minus 15 epsilon. So you get minus 39 epsilon minus 144 divided by 2 epsilon plus 12. Okay. Now you need to find out this value. So there are no values here, so this would be 0. And if you want to find out the last value in here, so it would be this value into 15 divided by this, so it will be 15. Now let us see the signs of all these numbers. So you have positive, then you have positive here again. Epsilon is considered greater than 0, so this is also positive. Now what might be the sign of this? Now let us limit epsilon go towards 0. Okay. So now if you divide numerator and denominator here by epsilon, which is positive, you get 2 plus 12 by epsilon divided by 1. And if limit epsilon tends to 0 is applied here, you get, this is already positive and this will be a large positive value. This will be infinity towards positive value. So this will be positive value ultimately. So again, this is also positive. Let us talk about this number. Epsilon into minus 39 epsilon minus 144 divided by 2 epsilon plus 12. Now if you divide numerator and denominator by epsilon square, so if we are dividing by epsilon square, which is again a positive number, you get minus 39 minus 144 by epsilon divided by, this is positive number and dividing it by epsilon will give us positive number. So I'm not writing whole number because I am just interested in the signature or the sign, not signature, the sign of this particular number. So basically we are interested in finding out the sign of this number. Minus 39 is negative, epsilon is positive, and minus 144 by some small positive number will give negative value, and this is also negative. So numerator is negative, that means this whole number has negative sign. Okay, and 15 is again positive, right? So you have positive, 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 then negative, and again then positive. So how many sign changes are there? This is the first sign change, okay, from positive to negative, and then again this is second sign change, negative to positive. So that means we have two sign changes, and hence there are two positive roots. Okay, remember this concept. So according to the Routh-Harris building, we found out that the given characteristic equation has two roots which lie on the right hand side of the S-plane. So correct answer is B. Correct answer is 2. Let us go forward and see problem number 3. So by properly choosing the value of K, the output CT of the system as shown can be made to oscillate sinusoidally at a frequency in radians per second of. So basically we need to find out the value of K first, and after choosing this value for certain value, this system is going to oscillate at a certain frequency only, okay, which will not decay. So systems might look like these. So this will be a decaying system, okay. So this will be decaying system. We don't want this system. System either might be like this. System might be unstable. So it will keep on increasing. So system might look like this also. So this is stable, this is unstable. And third kind of system would be, so as this is second order, this will keep oscillating, either be stable, unstable, or critically stable. In critically stable, we will get the same magnitude throughout. Okay, we'll get the same magnitude. And we are interested in finding out the frequency when the system is critically stable. So that's what this problem intends to ask. So basically, if you change the value of K, the system stability will change, because as you can see, the characteristic equation is S square plus S cube plus 5S square plus 4S, and when you make the closed loop system, you get characteristic equation plus A. Okay. Now, when you change the value of K, then the system stability is going to change, because the roots of this equation are going to change, and you will find different roots on the negative side of the S-plane, on the positive side of the S-plane, on the origin, and according to these roots, you are going to get different response. So we need to find out this kind of response, okay, for certain value of K. And after finding this kind of response, we actually need to find out the frequency by which this system is oscillating. That means the frequency of this signal. Now, don't get intimidated by this problem. This is a very tricky but easy problem. Okay. So let us look at the given problem. We have the given characteristic equation as S cube plus 5S square plus 4S plus A. Now I explained to you in the previous problem that in the Routh array you might find the first value. Let us say this is S raised to m, this is S raised to minus m minus 1, and this is S raised to m minus 2. So if you have A, B here, you are going to get 0 here. and you need to replace this 0 by epsilon. So when you get a value 0 here, this system is going to be critically stable. Okay. This system is stable, but this is known as critically stable because you got the value 0 here. In a previous problem, we saw there was epsilon, there was 0 coming, and that is why the system was either critically stable or unstable. In the previous problem, there were sign changes, so that system was unstable. But in this case, we need to find out such a case that the system is critically stable, and ultimately we get such a response. Okay. Now, when you get such response, when you have two complex roots on the imaginary axis of S-plane, like this, and this is the value omega, and then you get such response of the system. Okay. So when you get two roots on the imaginary axis, then you are bound to get a critically stable system with the frequency omega. So the value of the imaginary part of these roots give you the frequency value. Okay. So now let us build the Routh array and find out a k such that first column element becomes 0. And for that k, we will find the roots of this equation, and whatever two complex roots that we get, those complex roots imaginary part will give us the value of the frequency by which the signal is going to oscillate. Okay. So now let us just write the characteristic equation again and build the Routh array. So if you build the Routh array, you get, so let me build the Routh array. So you get 1, then 4, then you get 5 and 8. So for s has to 1's value, you need to get 5 into 4 minus k divided by 5. So you get 20 minus k divided by 5. For this system to be critically stable, this value here needs to be 0. For this value to be 0, you need k to be equal to 20. Okay. Now, for k equal to 20, you are going to get a critically stable value. And for critically stable system, you are going to get two roots on the imaginary axis. Now let us find out the roots of this equation. So you have s cube plus 5s square plus 4s plus 20 is equal to 0. Now let us factorize this. So you get s square common here, and then you get s plus 5. You get 4 common here, and you get s plus 5 is equal to 0. So roots of this equation are, according to these factorization, roots are plus minus 2j and minus 5. So one of the roots is on the left hand side and two roots are on imaginary axis as we saw. So on the imaginary axis you have 2j and minus 2j. So what is the magnitude of these two roots? It is equal to 2. And you know that this is nothing but the omega d frequency. Okay. So this is the value we are interested in, which is 2 radians per second. So in this case, the answer is B. So the given system for k is equal to 20, which was all upon us how to choose this value of k, will oscillate with the frequency of 2 radians per second. Okay, so answer is B. Let us go forward and see the problem number 4. So we are given a unity feedback system having an open loop gain as given. Okay, and the system becomes stable when Now first we need to convert this into closed loop function and see the closed loop characteristic equation. So we have given Gs and H of S. You need to find out. So this is unity feedback. So H of S is 1. This is nothing but G of S. So your transfer function becomes K into 1 minus S divided by 1 plus K into 1 minus S divided by 1 plus S. You also have 1 plus S. And if you solve this, you get K into 1 minus S divided by 1 plus S and K minus Ks. Okay. So now this is the characteristic equation. And if you just write it in orderly fashion, the characteristic equation of this system is S minus Ks plus 1 plus K, which is nothing but S into 1 minus K plus 1 plus K. So the coefficient of S is 1 minus K and the constant term is 1 plus K. Now if you are to build the Routh array here, you are going to put S raised to 1 and S raised to 0. So the values you have here are coefficient of S is 1 minus K and the next alternate value is nothing, and the coefficient of S raised to 0, that is constant term, is 1 plus K. Now for this system to be stable, you need all the signs of these two terms to be same. So that means 1 minus K should be greater than 1 and 1 plus K should be greater than 1, or both of them should be less than 1. So let us find out for any one of the conditions. In either cases, we are going to get the condition on K, because as you can see there is 1 minus K and 1 plus K. So this should be greater than 0 and this should be greater than 0. So if you shift K on this side, you get K less than 1, and if you shift this one on this side, you get K greater than minus 1. Okay, so if you draw a number line, okay, so this is minus 1 and this is 1. Now you want your value of K to be less than 1. So that means, let me use another color. Let me use yellow color. I'm not sure if you are going to see this, but see, these are the values. I'm sorry, let me use red color, which is easy for the eye. So this is the red part, which are the values of K minus, which are values of K which are less than 1. So this actually extends towards minus infinity, but at the same time you have your values to be greater than minus 1 also. So greater than means on the right hand side. So all the values on the right hand side and all the values on the left hand side of 1, all the values of right hand side of minus 1. So what a red part you see are the required values of K. Okay. So which is the option which actually specifies this? So basically, if mod of K to be greater than 1. So mod of K should not be greater than 1, because if K's value is say minus 2, mod of K will be 2, which is not the condition. K cannot be greater than 1, K cannot be less than 1. But mod of K to be less than 1 is the correct value, because this condition means K is either less than 1 or K is greater than minus 1. Okay. So answer here is option C. This is a little tricky problem. If you tried solving this problem yourself, you might make very silly mistakes of changing the signs and taking out the incorrect option. So you need to be very focused. This was asked in the electrical examination gate paper. So let us go to the next problem. Okay. So let us see the problem from root loci now. Let us see first problem on root loci. Okay. So the first question is, the open loop transfer function of a unity feedback control system is given. The centroid and angles of root locus asymptotes are respective. Now you know that in any root loci diagram, so if you have a root loci diagram, so you have three roots here. Okay, one, and I think these roots are complex, maybe these are complex. So, and there is one pole, maybe so let us say pole is here. Okay, so there are n number of root loci, different root loci, n number of root loci, and this n is nothing but the number of poles. So there are three poles, that means there are three different loci segments, and every root loci starts from a pole and terminates at a 0. There is one 0 and remaining two zeros are assumed to be at infinity. And these two root loci which travel from two of the poles and which travel towards infinity are called as asymptotes. Okay. Now we need to find out the point from which these asymptotes traverse, because these asymptotes travel or originate from a particular point. Okay, of course these two root loci which are going towards infinity start from the pole, of course, but they meet at a certain point and then they diverge and then they travel towards their destination. And infinity is everywhere. Okay, infinity is everywhere. At every direction infinity is present. So these root loci can travel at any direction. Say this, say this, say this, or in any direction these root loci can travel. So we need to find out the angle also by which these root loci travel towards infinity. So we need to find out a point. Let us say this is the point from which these root loci diverge and meet at a point and then divert at a certain angle. So this point from which the root loci meet and then diverge is called as centroid. Okay, and centroid value is given as summation of real parts of the poles. Okay, real poles minus summation of real zeros divided by number of poles minus number of zeros. So in this case, you have the summation of the real poles is nothing but minus 2. Okay. So if you find out the if you find out the poles here, so one of the pole is at 0, and if you find out the roots here, you get minus 2 plus minus root of 4 minus 8 divided by 2. Okay. So you have minus 1 plus minus 2 by. Okay. So this is not 2 here. This will be 1 again. So you have minus 1 plus minus j as the two complex roots, and one of the pole is at 0. So real part is minus 1 for two poles. So you get addition of these two poles. Real part is minus 2. Okay. Also you can see this, the addition of the roots is here and with the negative sign. So addition of real poles is minus 2 and addition of real zeros is also minus 2. Okay, so there is only one 0 at minus 2 and summation of p minus z. Okay, so this is actually minus of minus 2. So you'll get plus 2 here because real part is at minus 2 and this negative sign will make this plus 2, and p minus z is nothing but 2. So there are 3 minus 1 0. This gives you 0. So centroid is at 0. So 0 is the point from which these asymptotes will divert or meet. Okay, so centroid is at 0. So answer is either A or either C. Now let us find out the angle by which these travel towards infinity. Now this angle is given by following formula. So if there are n number of different asymptotes going towards infinity, so you have 2q plus 1 into 180 degree divided by p minus z. So this gives you the angle, and where q is nothing but 0, 1 till p minus z. So putting 0 will give you one of the value, putting 1 will give you another value. In this case p minus z is 2, so ultimately you are going to get 0 and 1 as two asymptotes which are traveling towards infinity. So first you put q is equal to 0, you will get one of the value, and then you put q is equal to 1, you will get another value. And p minus z is nothing but 2. So putting q is equal to 0 will give us 180 divided by 2, that is 90 degrees, and another value will be, putting q is equal to 1, we will get 3 by 2 into 180 degrees, which is nothing but 270 degrees. Okay, so 270 degrees is nothing but minus 90 degrees also. So option A is correct here. Centroid is 0 and angles of root locus asymptotes are respectively 90 and minus 90. Okay, so problem number 1's answer is A. Let us go to the problem number 2. The open loop transfer function is given by following expression, and the root locus diagram for this particular expression is, now we have 4 diagrams, 4 different roots, and we need to find out the correct root locus diagram. So ultimately first you need to check if all the roots are placed properly. Okay, so let us find out what are the roots. The zeros are at minus 1 and minus 3, and the poles are at some a plus jb or a plus j beta. So this is the a plus minus j beta. So there are complex roots. Here, as you can see, b square minus 4ac is less than 0. So there are complex roots present. And now let us find out where we see complex roots. So in this case there are complex roots, in this case also complex roots. In every case there are complex roots, but complex roots are opposite side of each other and symmetric to the real axis. Root locus is also symmetric to the real axis. So basically if you put a mirror on this I'm really sorry, let me erase. Okay, so if you are going to put a mirror on this particular axis, you should get the mirror image of this particular diagram. So root locus is symmetric across the real axis, and hence both these diagrams are not valid. So if this would be symmetric, the diagram would be like this, and in this case diagram would be like this. But diagram is not symmetric, hence this is not the answer and this is not the answer, as these complex roots are not just below each other, they occur in pair. That means answer is either A or answer is either C. Now another thing you see that the direction of the root loci is different. In one case the root loci are coming from the poles, and in another case the root loci are going towards the poles. But we know that root loci originate from the poles and travel towards the zeros. So in which case is the correct answer? So A is the correct answer, because in A the root loci are originating from the poles and going towards the zeros. In this case the diagram is wrong, as towards poles the root loci are traveling. So C is wrong, A is correct. Okay. So this is how you can find out the correct answer. Let us go to the problem number 3, wherein we have given figure shows root loci of the open loop transfer function g of s, h of s of a system. Consider the following inferences drawn from the figure. So there are 3 statements given and we need to find out which of the statements are correct from the given figure. Now you see the root loci diagram. Now we will read the statements and cross check. So it has no 0 is the first statement. Okay. So now if there are 2 poles as we see. Okay. So there are no other poles. And this is the root loci traveling towards one of the infinity. This is the root loci traveling towards negative infinity and positive infinity. Now we know that if there are n number of poles and there are m number of zeros, okay, then n minus m number of root loci travel towards infinity. They go towards infinity. Okay. So now we have 2 number of poles. So here n is equal to 2 as we have 2 poles and 2 root loci are traveling towards infinity. One is this, which is going towards infinity, and one is this. So there are 2 number of root loci which are traveling towards infinity, and we need to find out m, which means m is equal to 0. So it has no 0, that means there are no zeros. So this statement is correct. Let us find out the validation of statement 2. Let me erase everything. Okay. So it is a stable system. Is it a stable system? How can you find out a stable system? By looking at a root locus. If root locus has all the poles situated on the left hand side of the S-plane, the system will be stable. In this case, you have both the poles situated on the left hand side of S-plane. There is no pole on the right hand side. That means the system is also stable. So statement 2 is also correct. Also, we have asked if it is a second order system. Is it a second order system? So we can write the transfer function as there are 2 poles and no zeros. So basically you just have A and K and S plus A and S plus B. Is it a second order system? Yes, because the characteristic equation will be S square plus A plus B S plus A, and highest power is 2. That means the order of system is 2 and it is a second order system. So all the 3 statements are correct in this case, and hence the correct answer is A. Okay. Let us move towards problem number 4. Okay. So this is again a root loci problem. So the root locus of a unity feedback system is shown in figure, and we need to find out the open loop transfer function for this system. So now we are given a root loci, and from the root loci we need to build the open loop transfer function. Now even in the last problem we saw how many roots are there and where are they situated. We found out the transfer function, but we cannot find the exact values of the roots as it is not given, but we can always find the relative value. As we can see, there are certain poles and zeros located towards right and left of each other, so we can find out the number of roots which are less than zeros and number of roots which are less than poles and greater than them. So you can actually find out the relative transfer function, and we can arrive at the correct option by eliminating all the options. So we know that. So let me redraw this for you. One of the pole is at 0 and the diagram is like this. Let me use another color to show you this. Okay, so this is my root locus. You have a circle here and you have one pole given here. Then there is an arrow traveling towards this 0. There is an arrow going away towards infinity, this point. You also have the root loci part of the left hand side of this pole, which is at the origin. Okay, so this is again a part of root loci, and you see a part of root loci even on this side. Okay, and which is coming towards this point. So there must be a pole here. Okay, and this is a 0. These are two poles and a 0 at the infinity. So now you know that if there is one pole given, one pole is at infinity. That means there is one asymptote is there. That means you have two poles and 1 0. Okay, one of the pole is at s is equal to 0. Okay, and you have, let us say, a 0 at s is equal to b and a pole at s is equal to a. So transfer function of such kind is, basically, you know that the root loci travel from poles towards zeros. So these root loci travel from the poles and going towards a 0. That's why we have situated a pole here. So transfer function here in this case will be some k into a 0. So you have a 0 at, say, s is equal to, I'll just write minus b. That's why the value of 0 is minus b. So expression will be s plus b divided by s, which is a pole at 0, and another pole which is at s is equal to minus a, say minus a. And now there is only option B and option C which is of this kind. Okay. Now you need to find out the exact transfer function. As you can see, B is on the left hand side of A. That means B is actually minus B is right, the less value than minus A. So basically this can't be 1 and this can't be 2. Okay, I mean minus 1 and minus 2. So basically B is equal to 2 and A is equal to 1. And that is why you have the transfer function C. Okay, so you have k into s plus 2 divided by s into s plus 1 as a transfer function. You can see the relative values. That is why C is correct. Let us go towards problem number 5. Okay, so this is a very interesting problem. Keep attention into this problem. So in the given figure, the figure shows the root locus of open loop transfer function of a control system, and you have given the values PQ and PQ dash. So let me call this a PQ dash. So this PQ and PQ dash is equal to 2.6. Then you have RP is equal to 1.4. Then you have OR is equal to 2. So O is this origin. OR is equal to 2. Then you have OQ and OQ dash. OQ and OQ dash is equal to 1.4. Okay. So now you need to find out the value of forward path gain K at the point P. Okay. At point P you need to find out the forward path gain. So basically you can see the root locus is traveling from points Q and Q dash. Okay. So we can assume that there is a pole here and a pole here. If there is a pole here, there must be a pole here, because the root of omega square plus b square. So if you had two poles, then your magnitude will be the multiplication of two magnitudes. And magnitude is nothing but the distance between these 2 points. So from the pole, you need to find out the distance towards P. Okay. So the length of the vector QP into length of the vector Q dash P gives you the multiplication of magnitudes from the poles towards given point P. And in the numerator function, you have zeros. What is the zero given? R is a zero in this case. So the magnitude of the vector from P to R or R to P, length of the segment RP will give us the magnitude of the numerator function. There is no other zero, so we will just have length RP. If you find this out, we have given the length of PQ and PQ dash, which is nothing but 2.6 into 2.6 divided by length of RP. RP is nothing but 1.4. Okay. And if you calculate this, we already have K is equal to this. This will be equal to K, which is nothing but comes out to be as 4.28 something. Okay. So the only option correct is option D. I hope you have understood this problem. This is a very important problem. You found out the value of K from the given vectors or given magnitudes of the poles and zeros towards a particular point. So the correct answer is 4.8 in this case. We'll end this chapter here. I hope you have understood the concepts and these very meaningful problems in this session also. Please let me know of your feedback. We'll end this session here. Thank you.